Okay, we are on. So, today it's going to be another perspective of the beam design, that is the consideration of what the point load can do to our beam. That is, sometimes we say it's a local failure of the beam under the point load. Okay, now let me clarify one thing. There's no such thing as point load. To say you have a point load, is the load a point? Can you apply the load through a point? It's impossible, right? So even though we call it point load, it comes in shapes and form. But to call it with the true name, it's very, very long and it's very hard to pronounce. So that's why it becomes point load. But make no mistakes, there's no such thing as a true point load. Its official name is called concentrated load, okay? So point load is like an official name. You can call it point load, but in your mind, you must know that even though we call it a point load, it has dimension. Okay, now before I get into this stuff, let me try to give you a general perspective of what we have been dealing with the beam so far. Okay, so when you have the beam, when you have the beam, for example, generally beam, of course, you have to deal with flexure, right? And in flexure, you have the global buckling. But this time you have learned only one condition, that is your beam is sufficiently laterally braced. Okay, so now braced. Okay, and then local. That is the buckling of the flange or the web. But you, insofar, you should know that for hot roll, web is always compact. So it's safe to say that you generally check only flange. But for in terms of academic and in terms of professionalism, even though you know deep down inside that your web should be compact, you should always check it and provide evidence. Okay, that's the flexure aspect. And the second is, of course, shear. Now you should know when we talk about shear, generally we would mean flexural shear. Okay, and then it's the shear itself and the local buckling under shear as well. So we should always check to make sure that, in calculating the capacity, we can use that formula 0.6 Fy multiplied by the area, which means the CV is equal to 1. You should always check that. So that's two aspects. Now today you will be introduced the third aspect. Okay, additional. Not always, only when concentrated load is present. Okay, so when your beam has to carry what we call the concentrated load, or what you know as point load, there may be some additional possible failures that you need to consider. Okay, so with that said, we call that local failure. Okay, if let's say if your beam carries only the concentrated load, you will not need to check this. But let's say if there is a presence of a concentrated load somewhere on your beam, it may cause the local failure at that particular point where the load is applied. Okay, now this also includes the case when you have, say, a simple beam carrying the uniform load, but the beam is put on the support such that the support itself can produce the point load or the concentrated load coming in the form of the reactions of the beam itself. Now, if you have the reaction like this, it is considered a concentrated load as well, and local failure also may be applicable on your beam. Okay, so when you have the presence of the concentrated load, you need to perform an extra check. Okay, if you don't have it, you don't need to check it. And generally, local failure, there are two types of them that we will talk about today. The first one is called local web yielding, and the second is called local web crippling. Okay, it is always a nice idea to start with the local web yielding because it is a failure that we understand its mechanism pretty clearly. But for web clipping, even though it's there and it is the one that you know, the experienced engineers in the old days used to fear the most, it is quite difficult to have the mathematical explanation for it. So let me try to start with the local web yielding first. Okay, you may see the picture from the slide, but I think it's better that I start by drawing something for you first. So okay, let's say you have a beam. Okay, may not look as beautiful as I hope, but okay. So here's a beam. Let's say I have the concentrated load acting on it. Say this is the beam under consideration anywhere. You know, as I say, even though it is a concentrated load, or you may want to call point load because it is a lot easier to pronounce, it still has some dimension. Okay, it may be applied through the size of the plate. Okay, now in the old days they call this distance n. Okay, in the latest specification they change it into something like LC, but you know, it's the same thing. I don't remember exactly because you know, most of the slides they were based on the same old formula. It's the formula is the same, they just change the variable. Okay, anyway, this is the width of your so-called point load. Okay, that is the width n. Now, you know, you should know that when you apply the pressure on the surface, generally, if you look at any surface, let's say if it's a ground, okay? So if I apply the pressure on the ground like this, and let's say I'd like to see how much pressure at this region is going to be. You think the pressure will come down from the surface directly to the level below with a straight line contribution like that? The answer is no. It's only natural that when you press something, you know, the pressure will be distributed, you know, out wider. So that when you consider the area that is under this pressure, generally it should be bigger than the area that the pressure is on itself. Okay, so the question mark is, how much is this? That is the question that they had been asking, and they found the answer. All right, so again, let's say if this is the dimension n, and our concentrated load is applied on the beam, this pressure will be distributed into the critical area with the slope equal to 1/2.5. okay, on both sides. I don't know if my 2.5 is too small, but I keep saying it so that you know. If it's down 1, it's going to the side 2.5, okay? So if we know this distance, we should know how wide it is going out, okay? And we are saying this is the local web yielding. So the yielding should occur at the web. And that means that the yielding should occur right at the end of our fillet. Remember that this is the area of the fillet, which is pretty thick. My picture here is too small. If I try to write a bigger picture, you should see that if you have the flange, and then you have the fillet. Okay. Generally, if you pay attention, this distance fillet here is thicker than the thickness of the flange itself. Okay. This distance here, if we talk about the hot roll section based on TIS standard, this is R. Okay. If you look at the typical steel table in the market, they will give you the value R and then they call this T1, right? But if it is my engineering table that you guys have and should use, I call this TF. And I don't give R, but I give this distance in the table, which is the summation of TF and R, and I call it K. So when you have the section, you can look at the engineering table and use the value K. Now K is the distance where the yielding should occur, just right at the end of the fillet here. Okay, so that means if you know that this comes down with the distance K, this is K, you know. So therefore, naturally, this will be 2.5 K. Okay, and we have 2.5 K on the right side, and we can have 2.5 K on the left side as well. In the middle, we have N. So that means the area on the longitudinal axis is going to be equal to 5K plus N. That's the area where our beam can resist the concentrated load. Okay, that's the length. So if we multiply that by the width, what is the width? The width is, of course, the thickness of the web, TW, right? So now we know the length, now we know the thickness. So we can calculate the area of the beam web that will undertake the pressure from the concentrated load. So the area becomes 5K plus N multiplied by the thickness of the web. So we have the area. If we multiply the area with the stress, what do we get? The force, right? So ladies and gentlemen, if you look at the formula given by the AISC, you see that's the area, 5K plus N multiplied by the thickness. That becomes the area, and therefore the formula for calculating the local web yielding under concentrated load is this area multiplied by Fy, you see? So that's the area you will find, that's the formula you will find from the specification. Okay, is there any question? This is pretty straightforward. Let me try to erase this because I think I circled the T-web, okay? So you can see pretty clearly. Now, this, you can use this full formula. If the concentrated load is applied anywhere far away from the support, and the distance that you should consider is the distance should be greater than D. So as long as the concentrated load is applied with the distance greater than d away from the beam end. Let's say if this is my beam, and this, let's say if this is x, the location where your concentrated load is applied. If x is greater than d, you get this full formula. If this distance is less than d, that means you cannot have, you know, the area of the stress develop on both ends like this. You can only have the stress develop at one end. So you have to say, you know, discard this area. So if you can only have one side of the distribution, you can only have 2.5 K. That is why when the load is too near the end of the beam, you will only have the area of, you will only have the area from one side and then end. So that's why it becomes 2.5 K plus N when your concentrated load is near the end of the beam. Okay, the key is to locate the load. So you can have the load near the end of the beam, for example, the reaction of the beam itself. Okay, if I place the beam on the support and the reaction of that particular beam becomes the concentrated load, that reaction would be very near the end, and therefore you will only have like this area left. Okay, so that is local web local yielding. Any question? Now, because a little bit of history here, when they were looking for the local web yielding, actually they were looking for web crippling. They tried a lot of experiments to investigate the web crippling behavior of the beam, but sort of accidentally, they also found that the web could also fail under yielding as well. And somehow the crippling is always the more serious one and probably gonna govern most of the time. And therefore they say, you know, the factor of safety can be used for only 1.5. That's enough, okay? And that results in the reduction factor equal to 1. This is the only one case where the reduction factor is equal to 1 and factor of safety is equal to 1.5, notwithstanding the shear, which was, you know, sort of a mistake. Okay, so that's it. First failure is local web yielding. Okay, so let's move on to see the next one where it was the main target that they wanted to find out. Okay, the second one is called web crippling. Now, web crippling is this, literally. It's sort of buckling, but it's a buckling under the concentrated load, and sort of your beam web gives way, and it just like that. I cannot take it anymore. The load is applied here, you know, and it caused the beam web to buckle and lose the ability to carry the load anymore. Now, generally for web yielding, the concentrated load can be either tension or compression, you know. Let me write down. It can be either tension or compression. But for the web crippling, in order to cause this kind of behavior, we can say it has to be compression only. Okay, so they test, and you know, this is the formula that every time I talk about it, it's the formula that I am least proud to talk about because it's purely empirical. Now you guys should know the meaning of the word empirical by now, I suppose, or maybe not. Empirical, it's completely based on, you know, experimental data and curve fitting. There's no explanation as to why there's this term or that term in the formula. It's just what they had there, and it worked best in terms of curve fitting with the data that they got from the test. Okay, and again, they got two cases for, you know, the location of the load. When you have the concentrated load anywhere in the middle of the beam, but let's say X here, the location of the load, if X is greater than D over 2, not D like web yielding. If X is greater than D over 2, you get to use this formula. Okay, and it's a bit of a pain, and you may find it difficult to try to punch a calculator to get the right number. Oops. Here we go again. Let's wait for a moment. Okay, we're back in business. Okay, but so you have to be careful. Okay, notice that if the load is somewhere in the middle, you get the coefficient 0.8, and then it's T web square, N over D ratio. N is, of course, we already talked about, it's the width which the load is applied, and the rest is just typical. Notice that this crippling is a very critical failure, so we have reduction factor of 0.75 and factor of safety equal to 2. Now move on to the next case where the concentrated load is very near the support. Okay. Now when the load is near the support, you know, less than D over 2, you have two formulas based on the N over D ratio. So we have to check that if N over D is less than 0.2, you get to use the formula that looks similar to the one that you had before, but the coefficient is reduced from 0.8 to 0.4. But if N over D is greater than 0.2, you get this one. So there's no point beating around the bush. It is what it is, and the formulas are like this. And I always wonder myself why they don't try to change it, because this is the, you know, based on the old research, and therefore they would probably didn't have a very good say program or mathematical means to fit the curve better. That's why the formulas look kind of very unfriendly to use, but it works, and let's say it's not that difficult maybe, so they keep it. Okay, so that's it. The two extra failure modes that you guys need to check if your beams would have to carry the concentrated load, and you would have that. You know, remember that beam, the main beam. Okay. Wow, I don't know if you could design that yet. So, but let me say, maybe you guys could do this, you know. Remember the main beam in your grid on the second floor, where it's the main one that goes between the two columns, the longest one, and it has to support the column from the roof. Now that is a classic concentrated load. So you guys better check that. All right. And because tomorrow we will talk about the design of the column, so you would know the size of your column. Okay. And then once you have the size of the column, you would know the size of your base plate as well. Remember, last year I had the issue, a little bit of an upsetting issue with students, but I'm not upset with any of them. I understand that this is based on experience. But, when I say this, you guys gonna laugh, but then you do it yourself. You know what happened last year? What happened was this. When students were asked to design the base plate. Oh, I write it on the last page again. When students were asked to, let's continue on from this and then try to erase the one in the middle. When students were asked to design the base plate, they already got the size of the column. And then after they design the base plate, they don't care how big their columns were, so some would end up with the base plate smaller than the column, like this. How would you connect the column to the plate and then to other, structure? It's crazy. Some would, okay, this is my column and then my base plate. Let's put it right equal to the column. How would you connect your base plate to the column? The only means is to weld them, right? So how would you weld the flange of the column to the base plate here? That is impractical as well. So even though you get everything correct, your base plate is not going to fail. I got the right size and so and so, but the size that you decide to use cannot be constructed. So, if you don't know anything about the calculation and I give you the drawing to study, you would say, teacher, how can they fit the base plate? When the size of the plate is smaller than the column or it's equal to the column. You would, the designer is so silly. But you would do the same thing, believe me, if you are not careful and if you do not have the concentration to know what you are doing or what you are dealing with. Okay, so the proper way is just to have the size of the plate slightly bigger than the size of the column so that you can weld them around. So if on the next phase you design the size of the columns, you would know how wide this should be, and therefore you can sort of have some idea, not here, on the end term that you can use on your local web building and web crippling. Okay. All right. So that's it. Now we are done with the additional. It's time to learn another aspect that is somewhat related to the concentrated load. Okay, it's about the beam bearing and the column base plate design. Okay, generally you can have a situation where you must place the beam to sit on some other support. Generally, you cannot put the beam onto, let's say, if this is some kind of concrete support, you cannot put it on the concrete right away. You need another, sort of a go between structure so that you have the means to adjust the level of the beam. Generally, this, let's say if it's it doesn't have to be masonry, it can be anything. It can be a concrete foundation or concrete beams. Let's say this must come into place before, right? So you can install this plate onto the concrete structure underneath, and then you will have the bolt coming up here. It can be anchor bolts. If it is installed in the concrete and it looks like this, they call it a J bolt. If it is, you know, a typical one, you may call it the anchor bolt. Okay. Now the anchor bolts, you know, there are two types of them. The one that you install prior to the construction, which is the best if you could. That means you must know the location of your beam exactly, and therefore you sort of, you know, embed the door bars before you cast the concrete. But that has to be done before you cast the concrete. This is not my stuff, but it's for your own knowledge. Pre-install and post-install. This is before concrete casting. You get a very, very strong bolt because the bolt is in place, and then you cast the concrete to sort of, you know, hold it in place, embrace it in place. But it's difficult. And most of the time that cannot be done. So it has to be installed after the casting. So what does this mean? It means that if you cast the concrete and you think, I need a bolt here, it means you have to drill it. You have to drill the holes, and you need to use the anchor bolts, and you need to have some kind of a bonding between the anchors and the concrete. Now, generally, there are two kinds of bonding that you can have. The first one is called mechanical. Where the anchor bolt itself would have to find a way to hold on to the concrete, like having some sort of the anchor, you know. The mechanical could be something like, you know, after the installation, the anchor just goes down there, and the head just pops up to form something like this, so that, you know, the connection between the concrete and the bolt is strong. It's not going to be exactly like this, but you know what I mean. Another one is chemical. So that means you put the bolt in there and you use some kind of chemical admixture or something like that to create the bonding between the anchor bolts and the concrete. So, you know, regardless, it is impossible that the post-install should be as strong as the pre one. But, you know, circumstances that the pre-install, you need to have a very, very good planning. So you always know ahead of time where your beam is going to be, and therefore you can install that. But this will be like this if you have a very like big main beams that will be attached with the concrete columns, for example. Okay. And post-install, you're going to face that a lot if you need to, say, construct some structure onto the already existing one. Okay. So with that said, you know, we have two cases. First one is when you sit the beam on the concrete structure. So this is a case where, yes, the reaction of the beam will become the concentrated load, and therefore you need to check the beam web yielding and beam web crippling. Okay, this comes with the beam. And there are two extra failure modes that you need to check whenever you try to connect a steel structure to the concrete structure. First is called concrete crushing. Now it's fair to say that, you know, no matter what you do, the steel is stronger than concrete. And if you don't use high strength concrete, generally the strength difference between concrete and steel is like 10 times. So we need to be careful to make sure that the concrete will not crush under the load coming from steel. And we prevent the concrete crushing by, you know, giving the area that's going to be large enough. Remember what we do, it's all the force is equal to the stress multiplied by the area, right? If the stress is the strength of the concrete, which you cannot increase, you will have to make sure that the area that will support the load is big enough. And when you know the area of the concrete, that means the area of this plate. The area of the plate should be related to the area of the concrete underneath, right? So if you can prevent the concrete from crushing failure, it means that you should know the size of the plate that you need to support your beam. And when you know the size of the plate, the next is to make sure that the plate doesn't fail. And the failure mode of the plate is plate bending. This plate, under the concentrated load, the beam is pushing down and it has a concrete underneath. It means that the plate will be bent. And therefore, if we are going to prevent the plate from excessively bending, we need to figure out the thickness. If the plate is thick enough, it will not fail during under the bending. Okay, so it's of course it's pretty blunt, but you know the plate thickness. Or maybe I should say it's not the thickness here, but say modulus, because it's bending. Okay, if you know the modulus of the plate, you will know how thick your plate is going to be, because you know the size from the calculation of the area to prevent the concrete failure. Okay, so when I put the beam on the concrete support, there are aspects of the beam failure and of the, say, support failure. Okay, the two red ones are the failure of the support, which consists of concrete and the plate. The second is the failure of the beam itself. Okay, we already talked about the beam web yielding and the beam web crippling. Okay, so now let's move on to the failure of the concrete. Okay. Okay. I think I'm going to come back here, but let me try to talk about the concrete first. So, let's say if I have the concrete and I have the plate on top of the concrete. So let's say this blue one is the size of the steel plate that will be, say, put underneath the beam and on top of the concrete. So the stress will be on this area. But like the same thing as I talked about with the let's say the beam yielding. Okay, when you have the stress coming in like this, the stress will be distributed down below in the concrete. Okay, so if, let's say, if the area of the plate here is A1, the area of the concrete that will actually undertake the pressure is going to be bigger than A1, because the stress coming in like this, once it reaches the face of the concrete, it will be distributed outward like that. And somewhere down below, the failure will occur. So the question mark is again, what is this distribution? Okay, and unlike the distribution in the steel beam, where you have the ratio of 1 equal to 2.5, the concrete folks, they use the ratio of 1 to 1. So that means, the area of the concrete underneath here that will carry the load will be spread out equally on every side. So it's safe to say that, you know, this line should be 45 degrees, you know, spread out until it reaches the end. Okay, so I'd like to include this because the general idea is the same, where you have the pressure coming in, but this is not where the failure will occur. The failure will occur somewhere underneath. And therefore, we don't use A1 to calculate the area that the concrete will carry the load. Okay, and because, you know, I would like to create a video that the first session is steel and then the second session is about the concrete and the plate design. So I think I'm going to stop here, and let's say if you have any question, please do ask now. Okay, so as usual, so I'm going to stop the share. I am going to stop the record.